there. First speaker, second session this morning is David Baraglia from the Australian National University and the logical team of the
So I'll be talking about logical integrality with monotomy. Like, I think it's an interesting thing to look at. So, okay, here's a motivating idea for what we're going to do. Here's two versions of integrality which you might come across. One is topological integrality, and the basic ingredient here is principal torus bundles with a flux. And integrality here essentially exchanges the Chern class and the flux. So you have T deals with another principal torus bundle and integrality operation. And then another version of integrality, topological mirror symmetry. So the motivating idea is coming from the SYZ conjecture, and we have Baraglia that's fibers are special Lagrangian submanifold, then inevitably they're going to have singularities. So you have to try to understand how what's going on topologically with singularities. And so the idea is if you remove the singular fibers, you just get a torus bundle, although it has some monotomy when you go around the fibers. And so the duality construction is just take the dual monotomy, and then you have to do something to fill in the singular fibers. So there's a bit of work involved there. But the simple part is just dualizing the monotomy. So what I want to do is combine these two operations into one thing. So basically I'm only going to consider the monodromy aspect. So topological integrality is monodromy. The next step would be to include singularities as well. So that's work in progress. Alright, so the ingredient we're going to use to do this is affine torus bundles. So for principal torus bundles, we have transition functions which are translations, and for something with monodromy, we want general linear. So we want to combine this. So we take our vector space, which is just Rn, and inside is the standard lattice, torus equations. And so the group of affine transformations on the torus bundle is just this semi-direct product. So it's translations together with general linear. So an affine torus bundle is a torus bundle straight M, and the transition functions are valued in group F. And so the natural question is what torus bundles are affine torus bundles? And it's a fact that this inclusion is a homotopy equivalence for n less than equal to 3. So if the fibers are ranked less than equal to 3, then there's always an affine structure. So my understanding is this is not true for all n, although I have seen a couple of papers that claimed it was true, so I'm not quite sure. Anyway, the good thing about affine torus bundles is there's a pretty straightforward classification. So affine torus bundles are in bijection with equivalence classes of pairs, rho and Z. So rho is the monodromy, so it's a representation of the bundle group into a linear group. And C is a twisted Chern class. So for just a principal torus bundle, you get a Chern class H2 with coefficients in Zn. But in the affine case, what happens is you use this local system. So the pi 1 acts on the standard lattice Zn, and this gives you a local system, and that's where you get this Chern class. So the way you can see this is just a long exact sequence. So just think of a standard exponential sequence. You can do it. This is just a rank 1 case. You have a standard exponential sequence, and then you take sheaf cohomology, and that's what gives you the isomorphism isolative principal circle bundles and churn class? Well, you can do a similar thing with local coefficients. So these guys get twisted by some representation. This is where your churn class is. And the equivalence relation, which you mentioned earlier, the equivalence relation is essentially the action by GL and Z. So the GL and Z conjugates the monodromy, and then the corresponding isomorphism of the local coefficient groups. Alright, so first we're going to look at the rank 1 case. So we have E hat circle bundles on M. Alright, so in the rank 1 case, every circle bundle has an affine structure. And then flux, so H hat, and H3 with integral coefficients. And GL1Z is just Z2. So the monodromy representations are really elements of H1 coefficients in Z2. And we get this usual sort of diagram. We're going to be referring to these maps occasionally, so I'll just write it down. Right. So the definition of topological T-duality in this case is these two pairs are T-dual if. Okay, first of all, they have dual monodromy, but since we're in the rank 1 case, and the general linear group is just set, so it's just the color here. And then we have this interchange of churn classes and flux. So I should explain that there's a existing sequence of local coefficients. So sequence looks something like this. This is the rank 1 case. So this is cap product with the twisted chain class. Oh, actually, this would be the Z. Pull back. Right, so we have this existing map, which is pushed forward in cohomology, and because the fibers don't necessarily have a consistent orientation, that's how you pick up this local coefficient. And then the churn class is also valued in local coefficients, so when you do this cut, you're sharing the local coefficients and get back to it. That's the distance sequence. So what's going on here is push forward degree 3 classes are then degree 2 classes over here. And then this last condition is that when you pull back the flux on the hat, so the basic theorem here is that for any EH, T2, E hat, H hat, and unique up to isomorphism. So here, isomorphism means we're considering fiber bundle isomorphisms, and you pull back the flux. So it's important to say unique up to isomorphism, because fiber bundle isomorphisms of E or E hat will actually have a non-trivial effect on the cohomology. So you only get uniqueness once you factor out. Okay. So now for the general case, we consider E and E hat, which are affine Tn bundles on them, and H and H hat three classes again. So then we have monodromy representations, rho and rho hat. to get a T-dual, we're going to require a constraint on the flux. So, and a similar constraint on the channel. So if you look at the Leray spectral sequence for the vibration, M, you get a filtration in cohomology. So if this was over R, we could use differential forms, and then this filtration amounts to choose a connection, and then you can decompose into horizontal and vertical, and you're sort of counting the number of legs on the fiber. So the condition we want is that our H lies in F23, which translates to H has one leg on the fiber. So this F33, these are things pulled back from the base. So you think of as having no legs on the fiber, and then this is one leg, two legs, three legs. So we're only considering this much cohomology. If you go higher, then that's where things become complicated, and there's attempts to explain it using some sort of non-commutative chloride or even non-associative. I'm sticking in the purely classical sort of situation. Alright, so H is required to lie in F23, and you can project it to the quotient. So remember that the spectral sequence converges to the associated gradient space. So E2, infinity is this quotient. I don't think my notation is standard here. But, okay, so you get this element E21 infinity. And then E21 infinity is a sub-quotient of E21 on the second page, which is H2 M rho joule. So we're going to use this to define T-duality in this general case. So E and E hat are T-joules here. Rho and rho hat are joule representation. And then we have this swapping Chern class and flux with something a bit more complicated here. So remember that H lies in this associated gradient E infinity, and then we want that it's represented in E21 by the Chern class of the joule. And again, this condition of the flux coincides on the plus one.
Explain the road start to the end.
This is the Rankine case. So lambda with this lattice Zn, and then you get a local coefficient system by considering the representation. Okay, so the result here is that given this condition on the flux, there's always a T-joule, but it's not unique. In particular, the Chern class of the hat is not uniquely determined. You get this two-form shifts. Although it is interesting, when the monodrom is non-trivial, this group's going to be smaller than rho is trivial. So monodromy tends to reduce the ambiguity in the T-joule. Okay, so this is a rough steps of the proof. So you start by you choose your Chern class to mix H, and so you can find a pair like this, where you have this interchange Chern class of flux, and the main difficulty then is this condition that the flux coincides on the correspondence. So you look at the spectral sequence for the fiber product, and rho and rho had a dual representation, so the duality pairing, so you have this symplectic form representing the pairing in this space, which is essentially E02 in the spectral sequence. And then what happens is that the B2 of the spectral sequence maps omega to Chern class like this. So when you consider different, you get a term like this in the spectral sequence, and that gets killed by 2. So then you get something here which is the pullback from the base. So then you just adjust H so that you get that here. Alright, now twisted cohomology. So if we have residual pairs, we can consider their twisted cohomology. So we're going to assume everything's smooth and represent H by 3 forms. So then you have this twisted cohomology. So you take the ordinary ring of differential forms, and then you have this twisted differential, which is ordinary differential plus wedging with H. Okay, so if rho is valued in special linear, then you have an isomorphism, just like you do when there's no monodromy. And it's given by this kind of Fourier transform, where you pull back the form, you multiply by a certain 2 form, and then you integrate. So this 2 form in particular has the property that when you restrict it to the phi loop, it looks like the natural symplectic form of the product. But what if rho is not valued in special linear? Then there's a problem because this integration requires an orientation. So then what do? You let W1 be the determinant, which is W here, so you get a flat line bundle. And then we can consider a different version of twisted cohomology. So instead of differential forms, we tensor by this flat line bundle, and then we have a differential here, which is you get this differential using the flat connection, and then you also have wedging with the 3 form H. Okay, so then in the general cases you have these isomorphisms where the twisted cohomology without W1 equals twisted cohomology on the other side. General situation. Okay. Now twisted K theory. So the idea is twisted K theory represents D brane charge. So it should be an isomorphism between the twisted K theories. So our representation determines a flat vector bundle, and then we have W1 and W3 vector bundle. And so we're going to use a version of twisted K theory where the isomorphism buttons of twist this product H1 is Z and coefficient H3 is Z. So you might be more familiar with just twists in the H3, but you can get these other twists using, for instance, gradients of bundle curves. Okay, so then you have isomorphism in twisted K theory, but you pick up additional twists W1 and W3. Okay, but in the special case where your representation has W1, W3 trivial, which is precisely the condition that this flat vector bundle has a spin C structure, then you get this isomorphism of the twisted K theories in H. Okay, so here's the proof, and this is basically just a generalization of the proof given by Lincoln and Schick in the T-duality paper. So you represent H and H hat as bundle gerbs, and you can find an isomorphism between the bundle gerbs such that on the fibers, this isomorphism U looks like the Poincare line. So what that means is, so you choose trivializations of H and H hat on the fibers, and then on the pullback, so you pull back these trivializations and you get an isomorphism between pullbacks. Right? And if we compare this isomorphism with the isomorphism given by U, the difference determines an element of H2 on the fibers, and the requirement is that this element that we get is essentially the Poincare line bundle. Up to line bundles pulled back from the individual fibers. So with that condition, and you can always find such a U. With that condition, then you just do this Fourier-Mackay transformation. So pull back, and you apply U, and then you push forward. And then if we do push forward in twisted K theory, what happens is that you pick up this W1 and W3. So normally in K theory, to get a push forward, you're required to be spin C, which is when these vanish. Right. So if you restrict to the fibres, this transformation is essentially the Fourier-Mackay transformation in K-theory. So for this general situation of correspondence, you can, let's say the base is compact, and then we can just use minor V torus in the fibre element. Okay. So the conclusions are monodromy can be incorporated into topological duality in a pretty straightforward way, just using modular coefficient. Higher rank duality has the same sort of problems as it does when monodromy is not there. Although with monodromy it tends to make the T-dual less ambiguous. And the last conclusion is that we should consider DRAM cohomology and twisted K theory with not just this H3, but also these other twists. Okay.
Any questions?
I think I missed it at the beginning. If you take any special Gaussian vibration and divide it out and remove the singular fibers, will you always have a
Any questions? If not,
We have some good which has nothing to do with
Yeah, I mean, in my paper, I look at compact surfaces, and then you just consider basically, in that case, you can pretty much calculate all circles under there that are non-oriented. And then I've tried to calculate a few higher rank ones, and I got some partial results. But it's interesting though that you can calculate some K theory groups using T-duality. So you can even have like just an ordinary K theory group, and you can calculate it by calculating the twisted K theory on the T-dual. So yeah, that's interesting. You can use T-duality.
okay, that's completely